Square airplane windows once tore passenger jets apart mid-flight. Next time you're in a window seat at 35,000 feet, look at the glass. It's round. Well, a rounded rectangle with curving corners. Every commercial jet uses this shape. It's not for looks. Square windows literally ripped planes apart in the 1950s, killing everyone on board. It's the most expensive engineering lesson in aviation history, and it's hiding inches from your face right now. You need to understand what happens to a jet fuselage at altitude. Sea level air pressure is 14.7 pounds per square inch. Inside the cabin, it matches the outside. Balanced, but at 35,000 feet, outside pressure drops to 3.4 pounds. You'd pass out. So they pressurize the cabin. They pump air into that tube to simulate 8,000 feet. The inside pressure hits 11 pounds per square inch. That creates a massive pressure difference. The inside pushes outward with 8 pounds per square inch more than the outside pushes back. Sounds small, but spread across the fuselage, it's hundreds of thousands of pounds of force. It tries to blow the plane apart like a balloon, every takeoff, every landing. The fuselage expands when pressurized and contracts when depressurized. It inflates and deflates, over and over. This cycle is the pressure differential. It's the toughest structural load a jet fuselage has to survive, not turbulence, not hard landings, the repeated inflation of the cabin. Every time the plane pressurizes, the metal skin stretches. When it depressurizes, it relaxes. Stretch and relax enough times, and you get metal fatigue. It's the slow, invisible degradation of a material. In the early days of jet travel, nobody understood what it would do to a pressurized aircraft. Enter the de Havilland Comet. The world's first commercial jetliner. British. Beautiful. It entered service in 1952 with BOAC. It was the pride of post-war British aviation. The Comet flew higher and faster than anything before it, 40,000 feet at 500 miles per hour. It cut travel times in half. It was the future, and it had square windows. The Comet's windows weren't perfectly square. They had slightly rounded corners, but were basically rectangles with sharp 90-degree angles. There were also square cutouts for the radio antenna on the roof. Sharp corners in a pressurized metal tube concentrate stress. When the fuselage inflates, the stress doesn't spread evenly. It bunches up. It piles into the corners. Structural engineers call this stress concentration. Imagine a sheet of rubber with a square hole cut in it. Pull the rubber from all sides. The sharp corners act like wedges. The force bunches up right at that point. The stress at the corner can be 3 to 5 times higher than the surrounding material. 3 to 5 times. If your fuselage skin handles a certain pressure, the square window corners take several times that load. Every flight. That's exactly what happened to the Comet. On October 26, 1952, a Comet broke apart during takeoff. It was an empty ferry flight and the crew survived. The aircraft was destroyed. On March 3, 1953, a Comet crashed after takeoff from Karachi. 11 dead. On May 2, another crashed after takeoff from Calcutta, killing 43. Investigators initially blamed pilot error and weather, but the real catastrophe was coming. On January 10, 1954, BOAC Flight 781 left Rome for London. It was a Comet 1, registration GLYP. It climbed over the Mediterranean Sea near Elba. At 25,000 feet, the aircraft disintegrated. It broke apart in midair. The wreckage fell into the sea. 29 passengers and 6 crew died instantly. No distress call. Flying normally and then gone. They grounded the entire Comet fleet. The Royal Aircraft Establishment at Farnborough launched an enormous investigation. They recovered 70% of the aircraft from the seafloor. They rebuilt the fuselage piece by piece in a hangar. And they found it. A crack. It started at the corner of a square window. Specifically, the automatic direction finder window on the cabin roof. Just a square cutout in the pressurized hull. The crack started microscopic. Invisible to any visual inspection. It grew flight by flight as the cabin pressurized. Each cycle pushed the crack further. Then, over the Mediterranean at altitude, the crack hit critical length. The fuselage ripped open. The failure was so violent the jet broke apart in less than a second. Metal fatigue at a square corner destroyed the world's most advanced passenger jet. Investigators wanted proof. They took an entire comet fuselage and put it in a giant water tank. They pressurized it, depressurized it, over and over. They simulated thousands of flights. After 3,000 cycles, the fuselage failed. A crack formed at a square window corner and tore through the structure. Square corners in a pressurized fuselage are a death sentence. This changed aviation. The Comet was redesigned with rounded windows, smooth curves instead of sharp angles. The stress at the window edges dropped dramatically. The Comet returned to service but lost its market lead. Boeing and Douglas watched from across the Atlantic and took notes. The Boeing 707 entered service in 1958 with round windows. The Douglas DC-8 did the same. Every pressurized aircraft since the Comet disaster uses rounded windows. It's gospel. Why round? Why not oval? It comes down to how stress flows under pressure. A circle has no corners, no points for stress to concentrate. When a circular hole is cut into a plate and pulled, the stress flows around it smoothly, like water around a stone in a river. No sharp turns. The stress stays as even as possible. A circle is the optimal shape for a hole in a pressurized structure. In practice, most modern jet windows aren't perfectly circular. They're rounded rectangles, oval windows. They have 4 corners, but each has a generous radius. The corner radius must be large enough to keep stress below a critical threshold. A perfectly round window distributes stress perfectly. An oval window with well-designed corners does almost as well. The trade-off is oval windows give passengers a better view and let in more light. The Boeing 787 Dreamliner took this further. Its windows are 40% larger than the 767 it replaced. Still rounded rectangles, but bigger. Structural engineers made this possible by using carbon fiber composites for the fuselage instead of aluminum. Carbon composites have different fatigue properties. They don't crack the same way. This allowed larger cutouts without the same fatigue risk. Windows are this size and shape for another reason. Pressure. The window you look through isn't one pane. It's three separate layers of acrylic, each a structural barrier. The outer pane takes the full pressure load. The middle pane is the fail-safe. It takes over if the outer pane fails. The innermost pane, the one you scratch with your fingernail, is just a scratch shield. It carries no structural load. That tiny hole at the bottom of the window, it's in the middle pane. It's a bleed hole. It equalizes pressure between the outer and middle panes. The outer pane holds all the pressure. The bleed hole lets a small amount of air through so the middle pane isn't fighting it. If the outer pane cracks, pressure builds against the middle pane. It takes over. Every pane has to survive the same stress environment. Stress concentration applies to every opening in a pressurized structure. Not just windows, doors and access panels. Even rivet holes have specific spacing to distribute stress evenly. That's why aircraft doors are rounded at the top. It's why cargo doors have rounded corners. The entire fuselage manages where stress goes so it never piles up in one spot. This principle goes beyond aviation. Submarines face enormous external pressure. They have circular hulls and circular hatches. Industrial pressure vessels holding compressed gas are always cylindrical or spherical. Never boxy. You see it in nature. Bones have rounded transitions. Trees branch with smooth curves. Blood vessels curve gently. Avoiding sharp corners in loaded structures is universal. It was written in blood. Engineers use that phrase grimly but honestly. Modern engineering rules were learned through collapse, through loss of life. The Comet disasters killed 49 people across 2 crashes, plus 11 in Karachi. Those deaths brought an understanding of metal fatigue that has saved countless lives. Before the Comet, aircraft were designed for static strength. Can it hold the maximum load? After the Comet, engineers had to design for fatigue life. How many cycles before cracks form? This led to fail-safe design. If one component fails, the structure stays intact. Multiple load paths, redundant structure. All these ideas trace back to the Comet. Here's a detail often overlooked. The window that started the fatal crack on Flight 781 wasn't a passenger window. It was the automatic direction finder antenna window on the roof. A small, square cutout with slightly rounded corners. The ADF window was the worst offender because its corners were the sharpest. After the investigation, de Havilland redesigned every opening in the fuselage with much larger corner radii. They flew slower, so the fuselage experienced fewer cycles. The Comet was the first aircraft to combine high altitude, high pressurization, high speed, and high cycle frequency. It paid the price for being first. It's about learning from failure, building systems that absorb those lessons, making sure the same failure never happens again. Every safety feature you encounter exists because something went wrong first. Someone paid the price.